Today's lesson is on adding, subtracting, multiplying, and actually dividing radicals. And this is associated with our textbook lesson 6.2 to 6.3. So we're going to start off by simplifying radical expressions with addition or subtraction. And one thing to note is that when you have a common value underneath the radical, which is called the radicand, then it is a lot like simplifying with simplifying a variable expression. So for example, if I had 2x plus 5x, I would add these coefficients, 2 and 5, and the x would stay the same. So in this example number 1, since we have the same radicand, we can take the negative 5, subtract the 3, and get negative 8. And then the square root of 3 stays the same. Next, we have 2 radical 8 minus the square root of 8. We can put a 1 there, just like if we were subtracting a 6x minus x. We could think of that as a 1, so the 6 minus the 1 would be 5x. Here the 2 minus the 1 is 1. Square root of x, or simply written as radical x. So we can take a look at a few more examples here. Negative 4 square root of 6 minus 1 square root of 6. So that would be negative 5 square root of 6. Then of course we could add 3 terms, and so looking at this, negative 3 take away 3 would be negative 6. Negative 6 take away 3 would be negative 9. And we have the square root of 27. Something I didn't mention up above, we are not fully simplified here at the square root of 8 because 8 has a perfect square factor. So we could write this as 4 and 2 as the 2 factors and continue on down to 2 and 2. So we have a pair of 2's which would break free to the outside of the radical with 1, 2 left underneath. So the fully simplified form for number 2 would be 2 radical 2. And then for number 5, the square root of 27, we have 9 and 3, and then 3 can be broken into 3 times 3. So we've got the pair of 3's breaking free, so that would come out in front. So we'd have 3 times the negative 9 that's already there, and then that final 3 would stay underneath the radical, or 3 times the negative 9 is negative 27, square root of 3. So I'm just going to go down the page and do a few more examples. Here we change things up to radicands that have different values. So we're going to see if we can simplify those into a form that allows us to combine the like terms. Let's look at simplifying the square root of 45. So values that go into 45, factors of 45 would be 3 and 15. And then 15 could be simplified into 3 and 5. So here's a pair. So we could rewrite negative 2 radical 45 with that 3 out in front times the negative 2. And then left underneath would be a 5. So this becomes negative 6 square root of 5. Next we could simplify the square root of 20, which has factors 4 and 5. And then 4 has the factors 2 and 2, which can break free out in front of the radical as a 2. And we're doing 2 times negative 3, which is going to give us a negative 6. So let's just go ahead and write that as negative 6, or minus 6. And again, the 5 is left underneath the radical. And then minus 2 radical 6, the 6 has factors 3 and 2, which are both prime numbers, so that cannot be simplified any further, so we'll just have to leave that as minus 2 radical 6. So we can actually combine the negatives 6 radical 5 minus 6 radical 5 is negative 12 radical 5. And then minus 2 radical 6 would be our final answer. Let's go back up and try number 6 is a similar type problem. So let's take a look at 12. Can we simplify the square root of 12? So we'd break this into 3 and 4. 4 can be simplified into, or can be factored into 2 and 2, which is our pair. 2 then comes out front. We multiply 2 times negative 3 to get negative 6. The 3 is left underneath the radical. And then we have plus 3 radical 3. 3 is already prime, so we cannot simplify that further. And 20, square root of 20, well, we actually just did that one right here. So the 2 came out front, and the 5 stayed underneath. So this would become 2 times 3, which is 6, radical 5. Combining our like radicals, negative 6 plus 3 is negative 3, radical 3 plus 6, radical 5 would be our simplified answer. Let's take a look at number 12. So in case our index is something a little bit different, we can try to simplify this expression. So we have a 2 cube root of 6, and notice there's a cube root of 6 here. Or sorry, there's a 6th root of 6 here, and a 6th root of 384 here. So what I'm wondering is there a 6 as a factor of 384 that would be left underneath? Let's try it. So we would do 384 in your calculator. 384 divided by 6, and we get 64. Which works out nicely since that's a perfect square. Breaks into our pair of 8s, which would come out front. So I could rewrite this final radical expression. Ooh, sorry, we're looking at 6th roots. So we actually need, instead of a pair, we need 6. So we're going to keep going. This would be 4 and 2, 4 and 2. And then 2 breaks down, factors into 2 and 2, 2 and 2. So we have 1, 2, 3, 4, 5, 6 2's, which works out since this is a 6th root. So one single 2 will come out. We can rewrite this expression as minus 2 times the 3 times the 6th root of 6, or negative 6 times the 6th root of 6. So let's go ahead and see what we combine here. I've got 2 times the cube root of 6, and I've got plus 3 times the cube root of 6. So that's going to give me 5 cube root of 6. Next I have minus the 6th root of 6, and then minus 6 times the 6th root of 6. So this is like a negative 1 and a negative 6. So it's going to be a minus 7 times the 6th root of 6. Let's take a look at some more examples here. These are multiplication, so we have now a slightly different set of properties. We would multiply these radicands, multiply the values underneath, and then we can simplify. So we have the cubed root, so the index stays the same, and then we multiply the radicands and get negative 60. So to simplify this radical, we want to figure out, are there any triples? So we could write this as 12 times 5. And we'll consider the negative at the very end, so don't forget about that negative sign. 12 has factors 3 and 4. 4 has factors 2 and 2. And it doesn't look like we have any triples. So our final answer is just the cubed root of negative 60. Number 14, we have square root of 5 times the square root of 3, which is just the square root of 15. These are both prime, so I know that 15, square root of 15 cannot be simplified. Next we have the square root of 6 times the square root of 2, which is the square root of 12, and on the front we already simplified the square root of 12. It has factors 4 and 3. 4 is a perfect square. It can be factored into 2 and 2. The 2 breaks free and the 3 stays underneath. So we multiplied and then we simplified. Lastly, cube root of 3 times 9, so we have cube root of 27. Maybe you recognize that. Maybe you see the parts. 27 can be factored into 9 and 3, 3 and 3. And we need a triple again because the index is 3. So we can actually just rewrite this as 3. There's nothing left over. The cube root of 27 is 3. And then finally, we're talking about dividing radical expressions. So to divide radical expressions, we can rewrite this as, let's see here. So the square root of 15 over the square root of 20 can be combined into one radical, and we can just put our 1/5 out in front. Now we look at 15 and 20 and find a common factor of 5. Their greatest common factor is 5. So we could write 1/5 times the square root, so that would be 3 over 4. And now we could rewrite this as, so the square root of 3 over the square root of 4. The square root of 4 is a perfect square, which is 2. So we're going to go ahead and multiply this piece times this piece from the beginning. And we wind up with 1 times radical 3, which is radical 3, over 5 times 2, which is 10. Let's try another one. We have the square root of 8 over the square root of 100. We know these have a common factor of 4, greatest common factor of 4, 8. So we could write that as one large radical, or we could just apply that principle. So we wind up with a square root of 2 over the square root of 25. We can simplify the square root of 25 to be 5. And that's our final simplified answer. Now one thing to note, the denominator of a fraction cannot include a radical sign. And that's super important. So far we've gotten lucky and we've had perfect squares in the denominators. But we'll see some questions here where we have to what's called rationalize the denominator. So at number 5 here, 4 divided by radical 5. There's nothing to simplify, right? We only have the square root in the denominator. And we need to get rid of that. It's not a perfect square. So the way that we handle that is to multiply it times itself. And if we multiply the denominator by radical 5, we also need to multiply the numerator by radical 5. And that then does not change the value of the fraction. It'll just change the look of the fraction. Since the square root of 5 over the square root of 5 is 1, so you can kind of make that look like a 1. And 1 times any number is just that number. So this will wind up being 4 times the square root of 5 over the square root of 5 times itself, or squared, which simplifies into, these cancel out, just a 5. Similarly, in number 6, we cannot reduce, but we do need to get rid of the radical that's in the denominator, and we do that by what's called rationalizing the denominator, and multiply the numerator and denominator by radical 3. So now in the numerator I have a square root of 12. In the denominator, radical 3 times radical 3, like we saw here, I showed the work, but it was just 5. So the square root of 3 times the square root of 3 is just 3, and the 5 is there. So two things get simplified from this step to the final step. The 5 times 3 becomes 15, and the square root of 12, we've done that several times now, the square root of 12 is equal to 2 radical 3. Not a bad idea to commit that one to memory, since we do see it so often. When you see a square root of 12, it simplifies to 2 times the square root of 3. And that's all we can do. It might be tempting to look at the 3 and the 15 and try and reduce that further, but since the 3 is under the radical and the 15 is not, we cannot simplify that any further. Let's do one more example of rationalizing the denominator. Here we see radical 5 over radical 3. We try and simplify. We notice we can't reduce that, so we multiply numerator and denominator again by radical 3. Radical 5 times radical 3 is square root of 15. Square root of 3 times square root of 3 is 3. Square root of 15 doesn't have any perfect square factors. We already discussed that here in number 14. So our final answer is radical 15 over 3. And that pretty much sums up our lesson on adding, subtracting, multiplying, and dividing radical expressions.